In the year 1826, Sir Humphrey Davy, as President of the Royal Society, presented Mr. John Dalton with a Royal Medal for his development of the theory of definite proportions, usually called the atomic theory of chemistry. This presentation set an official seal upon the emergence as a scientific theory of an idea of matter which had existed for over 2,000 years as a belief, unsupported by experimental proof. In Dalton's time, chemistry was becoming an exact science, thanks to accurate methods of weighing and analysis introduced in the 18th century. Dalton was able to work out fairly accurately the relative combining weights of many elements. In his new system of chemical philosophy, published in 1808, Dalton pointed out that these combining weights, which are constant for each particular compound, must be related to the weights of the ultimate particles or atoms of the combining elements. Thus the atomic theory was reborn. According to Dalton, matter is composed of small particles which cannot be split up any smaller. These particles he called atoms. Our diagrams illustrate his ideas, but not, of course, the real shapes of atoms. He believed, secondly, that all atoms of one element are exactly alike and differ from the atoms of other elements and have a characteristic relative weight. Thirdly, he believed that atoms are indestructible and cannot be created. Fourthly, that chemical combination occurs between small whole numbers of atoms. Such combinations of atoms are now called molecules. In any given compound, all molecules are alike. Dalton invented a system of symbols to represent the atoms of the different elements. He used these to show how the atoms combined to form molecules. Though some of his conclusions proved wrong, atomic theory was the foundation upon which the chemistry of the 19th century was built. Painstaking chemical analysis based on Dalton's theory and research arising out of Avogadro's hypothesis concerning molecules in gases enabled accurate atomic weights to be assigned to the elements. A connection was sought between atomic weights and chemical properties, and in 1869 this was supplied by Mendeleev's periodic table, which arranged all the elements then known in families according to their atomic weights and properties. Thus, the column headed by carbon contains a group of elements with mostly similar properties. The next column contains another group of similar elements, and so on. Now, from left to right, the elements are arranged in ascending order of atomic weight. The whole table fits together like a puzzle. The properties and place in the table of unknown elements were predicted, and the discoveries of later years proved the accuracy of these forecasts. The decomposition of solutions by an electric current was used as a means of chemical analysis in the early 19th century. By careful measurement, Michael Faraday was able to show that in such cases a definite quantity of electricity was associated with definite amounts of the elements produced at the electrodes, that is, with definite numbers of atoms. Hence he suspected that electricity itself might be atomic by nature. It was established that there were two kinds of electricity. Unlike charges attracted each other. Like charges repelled each other. By convention, these two kinds of electric charge became known as positive and negative. In a solution like common salt in water, the sodium chloride exists as ions or charged atoms of sodium and chlorine. When the solution is electrolyzed, the positive sodium ions travel towards the cathode and the negative chlorine ions to the anode. The work of many scientists on liquids and gases led to the theory that in all matter, molecules are in a state of perpetual motion. The botanist Robert Brown was the first to see in his microscope what is now called Brownian motion. This is the intricate motion imparted to fine particles in suspension in a liquid by the impact of molecules. One can imagine the tiny particles being pushed about by these ceaselessly active molecules. Each molecule is so small that 27 million are contained in 1 cc of gas at 0 degrees centigrade and normal pressure. The thinnest soap bubble that can be made by ordinary means is about 1/100,000th of a centimetre thick. In this space, about 1,000 molecules could lie side by side. Each of these molecules would be 3 or 4 times the size of a small atom. This much was known at the close of the 19th century, which Lord Rutherford sums up in these words.
At the close of the 19th century, the labours of the chemist had resolved the matter of our material world into 80 or more distinct elements, and the atoms of these elements appeared to be permanent and indestructible by the forces then at our command.
The physicists of the 19th century were not less active than the chemists. Faraday investigated the conduction of electricity by liquids. Later scientists investigated the passage of electric currents through gases at low pressures with this kind of apparatus. Air is pumped from the tube until a luminous discharge passes from cathode to anode. As evacuation proceeds, brilliant rays are seen streaming from the cathode. The rays become invisible as pressure is reduced, but they still cause a faint green glow on the walls of the tube. This bell-shaped vessel shows the behaviour of the cathode rays more clearly. At first, the current passes from the cathode to the edge of a fluorescent screen beneath it. Next, the glow of the cathode rays is clearly seen around the cathode itself. As the pressure continues to fall, the rays will disappear, but their presence is revealed by a powerful green glow where they strike the fluorescent screen. These cathode rays can be made to cast a shadow of an object in their path. This proves that they travel in straight lines from the cathode. The rays are capable of transmitting energy. The little vanes in this tube are turned by energy supplied from the motion of the tiny particles rushing up from the glowing cathode beneath. It can be proved that the rays are negatively charged. A wire connected to a plate on which the rays fall will discharge a positively charged electroscope. In 1897, Sir J.J. Thomson devised an apparatus to measure the ratio of charge to mass of these particles, which had been named electrons. He was able to make an estimate of the actual mass of the electron. In this apparatus, A luminous spot showed where the electron beam from the cathode fell on a fluorescent coating on the end of the tube. This beam could be deflected in one direction by an electrostatic field between charged plates, and in the other direction by a magnetic field. These fields could be adjusted to balance each other, and from their strength the velocity of the particles could be calculated. Then, from the strength of the magnetic field alone and the deflection caused by it, the ratio of charge to mass could be found. From experiments such as these, the mass of the electron has been estimated at 1/1840th of the mass of the hydrogen atom. Sir J.J. Thomson's own description of this tiny object has been preserved for us.
Could anything at first sight seem more impractical than a body which can only exist in vessels from which all but a minute fraction of the air has been extracted, which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen, which itself is so small that a crowd of these atoms, equal in number to the population of the whole world, would be too small to have been detected by any means then known to science.
Thus the existence of a negatively charged subatomic particle, the electron, was established beyond all doubt. It was even found possible to photograph the track of an electron. This was done by an ingenious apparatus invented by Professor C.T.R. Wilson. During the war, most people saw the vapor trails left by high-flying aircraft. Wilson, while investigating the ionization of gases by charged particles, built a chamber in which such particles could be made to leave a vapor trail. It consisted of a glass-topped chamber filled with moist air. The bottom of the chamber is really a piston head, supported by the air beneath. Connected by a valve to the main apparatus is a large vacuum chamber. When the valve is opened, the air beneath the piston is sucked into the vacuum, and the piston drops sharply, creating an expansion of the moist air so that a cloud is formed. Now a charged particle from a source of radiation entering the chamber will ionize the gas along its path. Because of the sudden expansion, drops of moisture will condense on the charged atoms or ions along the path of the radiation and leave a visible trail. This is photographed by a synchronized electric flash. This apparatus, much improved since the original model, has proved invaluable in atomic research. Today, the electron is a commonplace. Any metal raised to red heat gives off electrons. The stream of electrons from this hot filament can discharge an electroscope. This is made use of in the radio valve, where the electrons from the hot filament can be used to send and detect signals broadcast over long distances. On this radar screen, electrons act as the eyes of a ship as it makes its way down the crowded river to the sea. And on the television screen, electrons paint pictures for our amusement.
The electron owes its practical utility to its smallness. It might have parodied Shakespeare, say, my use is great because I am so small.
The discovery of electrons raised big problems. Ordinary matter is neutral. For instance, it has no effect on an electroscope. Yet the cathode in this discharge tube can give off negative particles much smaller than atoms, which can turn the disc beneath. Some sort of electrical equilibrium has been upset by this emission of negative electrons from neutral matter. Surely positively charged particles must have been left behind. Investigation of the so-called canal rays, first discovered by Goldstein in 1886, proved that this conjecture was true. If a series of small slits be pierced in the cathode of a gas-filled tube, a luminous ray can be seen streaming in the opposite direction to the cathode rays. These rays were subsequently found to be positively charged. Sir J.J. Thomson used this discovery to build an apparatus in which the mass of the rays could be measured. A fine beam of positive rays was directed onto a photographic plate. A magnetic field produced a deflection of the beam horizontally. Similarly, an electrostatic field produced a vertical deflection. In both cases, the different velocities of individual particles produced a line instead of a spot. If both fields were applied simultaneously, the particles fell on the plate in a parabola. The position of this parabola in relation to that of the undeflected spot was determined solely by the ratio of mass to charge. Thomson was able to calculate the mass of these particles. He found that each particular kind of positive ray consisted of charged atoms of the gas present in the discharge tube. Under certain conditions, the different types of glow due to positive and cathode rays can both be seen. These phenomena could only be explained by supposing that the neutral atom contained both positive and negative charges in equilibrium. The stream of electrons from the cathode detaches other electrons from the atoms of the gas through which they pass. These atoms immediately become positively charged and rush towards the cathode. If the cathode is pierced, they emerge as positive rays. The sequence of events resembles electrolysis, and these charged atoms of gas are called ions. A gas in which such conditions arise is said to be ionized. In 1896, Röntgen found that the green glow excited by cathode rays striking the glass was itself giving off rays which caused a fluorescent screen to become luminous. The rays could penetrate light metals, but not dense material like lead. The center piece of metal here is lead. The outer ones are aluminium. Lead stops the rays completely, but the lighter elements are penetrated and cast a lighter shadow. These powerful rays became known as X-rays, and doctors soon found that they could use shadowgraphs made with X-rays to see inside the human body. Dentists were able to study the internal structure of teeth. And industrial X-ray machines such as this one have been developed to search for hidden defects. But in 1896, inquiry turned to the fluorescence produced by X-rays in certain minerals. The French scientist Becquerel investigated whether fluorescent substances could in turn give off X-rays. He placed a metal medallion on top of an unexposed photographic plate still wrapped in black paper. Next he shook onto black paper a quantity of a fluorescent salt of uranium and placed it over the medallion. Some time later, he developed the plate and made a print. Radiation from the uranium had produced an image of the medallion. Becquerel had discovered radioactivity. This radiation was discovered to be a property of any mineral containing uranium. Among such minerals are autunite, torbanite, and in particular pitchblende, which was found to be more active than uranium itself. The radioactivity in this pitchblende ore has revealed itself by its action on a photographic plate. Pioneers in this new field of investigation were Marie Curie and her husband Pierre. By sheer hard labor, she succeeded in isolating from many tons of pitchblende residue a fraction of a gram of an intensely radioactive substance. An exhaustive series of measurements and tests left no doubt that a new element had been discovered, more radioactive than any before known. The Curies called it radium and devoted the rest of their lives to the study of radioactivity. The power of this radiation from radium is easily shown. The scrap of radium embedded in this lead capsule ionizes the air to such an extent that the charge on the electroscope leaks away. The complex nature of this radiation from radioactive substances was revealed by recording on a photographic plate its behavior in a magnetic field. A fairly weak magnetic field produced a deflection of light charged particles called beta rays. A very strong field caused further deflection of the beta rays and, in the opposite direction, a deflection of heavier charged particles, the so-called alpha rays. There remained a penetrating radiation unaffected by the magnetic field, the gamma rays. By 1902, the alpha ray was known to be a type of positive ray, the beta ray to consist of electrons, and the gamma rays to be electromagnetic waves, similar to X-rays. Curie and Laborde discovered that the rays from radium can manifest their energy in the form of heat. Here are two Dewar flasks in which are tubes containing a radium salt on the left and a barium salt on the right. The barium flask also contains a coil of known resistance, which can be used to raise the temperature in the flask. Both flasks have thermometers. At the start of the experiment, the left-hand thermometer shows a higher reading owing to the heat from the radium. Next, an electric current is put through the heating coil. The heat from the radium is calculated from the amount of electricity used to raise the barium to the same temperature as the radium. Such experiments gave an inkling of the great energy locked in the atom. 3 years after the discovery of radioactivity by Becquerel, Rutherford enclosed a radioactive gas called radon in a thin-walled glass tube, which was surrounded by an outer tube from which all the air had been exhausted. The alpha rays coming from the gas penetrated the thin glass and collected in the outer tube. After a few hours, it was found that the outer tube contained the gas helium. Therefore, the alpha particles were atoms of helium, and this was the first direct evidence of one kind of atom actually changing into another.
A great change in our ideas resulted from the discovery of the electron and of the spontaneous radioactivity observed in the heavy elements, uranium and thorium. Soddy and I were able to show in 1903 that radioactivity was a sign and measure of the instability of atoms, and that the atoms of uranium and thorium were undergoing a series of spontaneous transformations.
Uranium, for instance, during its transformation to lead, gives rise to a whole new series of unstable elements, which ultimately break down into lead. The rate of change from one element to another may vary from a fraction of a second to millions of years. Only a few elements are normally radioactive. The majority are completely stable.
The next problem was to examine whether means could be found to break up the stable elements by artificial methods. Before this could be attempted with any chance of success, it was necessary to have a clearer conception of the structure of atoms. The idea of the nuclear structure of atoms, which I suggested in 1911, has proved very useful for this purpose.
Experimental evidence supported Rutherford's idea. Alpha particles from a radioactive source, if limited by a thin slit, will throw its image sharply on a fluorescent screen. A sheet of gold foil placed in the path of the rays causes a blurred image of the slit owing to the scattering of alpha particles by the heavy atoms of gold. Geiger and Marsden investigated the nature and extent of this scattering. In the apparatus first used, the source and scattering foil were stationary inside an evacuated metal box, while the fluorescent screen with a microscope attached was free to move on a graduated circular platform. Scattering of alpha particles continued to be observed as the screen and eyepiece rotated through an increasingly large angle. Only a powerful field of force could produce such deflections of heavy charged particles. Rutherford visualized a small particle in the center of the atom carrying a heavy positive charge. Since the majority of alpha rays pass straight through, he deduced that these positive particles were small and widely separated. In 1911, he propounded his theory of the nuclear atom. The atom, he said, had a small positively charged nucleus. Round this, the electrons revolved. The charge on the nucleus exactly offset the charges on the electrons. The Danish physicist Niels Bohr developed Rutherford's theory. Here are some models of the elaborate orbits for planetary electrons which Bohr and others worked out by using the quantum theory and certain bold assumptions of their own. This is the atom of lithium, one of the lighter elements. And this the simplest atom of all, hydrogen, with one electron revolving round the nucleus. They first worked out possible orbits for the single electron of the hydrogen atom. They varied from circles to various ellipses. The conception became more difficult when it was realized that these elliptical orbits themselves rotated, something like this. The structure of the atom increases in complexity as we pass from the simple hydrogen atom to helium with its 2 electrons in the same ring or shell, lithium with a 3rd electron in an outer shell, beryllium with 4 electrons, and so on. Wilson's cloud chamber provided experimental proof of the nuclear atom theory. Here are the tracks of alpha particles at the moment of formation. Each of these tracks marks the path of a single alpha particle, a helium atom stripped of its electrons. Photographs show that the tracks are straight and heavily defined because of the velocity and relatively large mass of these particles. Yet some alpha tracks showed abrupt kinks caused by some force powerful enough to deflect the heavy alpha particle. These kinks show where an atomic nucleus has deflected the alpha particle. Other photographs showed tracks ending with little forks. It was realized that these were made by particles after direct hits had been scored on atomic nuclei. Billiard balls can be used to illustrate a collision between particles of roughly the same mass. The white ball represents an atomic nucleus, the black an alpha particle. When the black ball strikes the white, both are deflected and branch off on different tracks. This is the sort of thing the cloud chamber photograph shows. The existence of the atomic nucleus having been proved, the next thing was to find out the magnitude of the charge on it. To see how this was done, we must turn again to X-rays. We have already seen how X-rays are caused when electrons fall upon any substance. X-ray tubes were built with a target on which the electron beam fell, causing X-rays to be given off at a convenient angle. About 1912, it was found that X-rays could be diffracted by a crystal, just as light is diffracted by a ruled grating. H.G. Moseley used this discovery to build an apparatus to obtain X-ray spectra of different elements. The electron beam was directed downwards from the cathode onto the target, carried on a little trolley beneath. X-rays were given off from the target. A crystal enclosed in a vacuum chamber was so arranged that the X-rays passing through a slit struck the face of the crystal. From the crystal face, an X-ray spectrum was thrown onto the photographic plate. Moseley found that each element used as a target gave off radiation, which included an X-ray of a characteristic wavelength. The X-ray spectra showed that this characteristic wavelength increased smoothly throughout the periodic system according to a simple law. The wavelength could be specified by a number, Q, which increased by 1 each time he passed from one element to the next. The elements had already been arranged in a table according to their increasing chemical mass. Moseley related his Q numbers to these atomic numbers. He deduced that there was in the atom a fundamental quantity which increased by regular steps from one element to the next, and that this quantity could only be the charge on the positive nucleus. Thus, the number of each element in the table, the atomic number as it is called, acquired a new significance. It indicated the positive charge on the nucleus of an atom, equal, though opposite in sign, to the number of orbital electrons in the particular atom. Of all atoms, hydrogen has the simplest structure, a nucleus and one electron. This nucleus, with its single positive charge, was christened by Lord Rutherford the proton. At this time, Rutherford was investigating the possibility of actually transforming atoms.
It became clear that to effect a veritable transformation of an atom, it was necessary to change the charge or mass of a nucleus, or both together. Now, the minute nuclei of atoms are held together by powerful forces, and to effect their disintegration, it seemed likely that a very concentrated source of energy must be applied to the individual atom. The bombardment of the nuclei by the energetic alpha particles from radium appeared to be the most promising method for such a purpose.
In 1919, Rutherford found that nitrogen nuclei could be transformed by bombarding them with swift alpha particles, and that protons were ejected at high speed as a result. In effect, he added together helium and nitrogen and changed them into oxygen and hydrogen. This was transmutation, the dream of the alchemists, to which the nuclear theory had at last given substance. Most significant of all, there could be no doubt that the proton, the hydrogen nucleus, was a fundamental particle in all atoms, the positive counterpart of the negative electron. How was the atom built up from these atomic bricks? Let us go back to our table of the elements. The atomic numbers represent the charge on the nucleus and also number the elements according to their increasing atomic weight. Now consider these atomic weights: 1 for hydrogen, 4 for helium, 7 for lithium, and so on. Our figures are approximations to the nearest whole number, but they show that in most cases atomic weights are at least twice as great as the atomic number. How could this difference between mass and charge be accounted for? Consider the atom of one element, say lithium. It has 3 electrons circling round a nucleus. This nucleus, we know, must have a positive charge of 3. So we put 3 protons in the nucleus. Each has a charge of 1 and a mass of 1. But the atomic weight of lithium is 7 approximately. So the nucleus must have 4 more protons added to it to give a mass of 7. Now we have upset the balance of the charge. 7 protons, 7 positive charges. 3 electrons, 3 negative charges. There is only one way to correct this. 4 electrons must be added. Now our charges balance. The negative charge from the 3 electrons is balanced by the outstanding positive charge of 3 on the nucleus. Such was the theory. But even in 1920, Rutherford suggested that there might be a neutral particle with the same mass as a proton, which could account for the extra mass without affecting the charge. Ultimately, this proved to be another instance of his amazing insight. But in the years between, the drive to penetrate the secrets of the nucleus continued unabated. From 1920 onwards, many other scientists pursued what opened up by Lord Rutherford's transmutation nitrogen to oxygen. Steady accumulation of data went hand in hand with improvement of apparatus. In this little instrument, a needle carrying a speck of radium is fixed in front of a fluorescent screen. Through a magnifying lens, the screen can be seen to twinkle with tiny points of light. Alpha particles cause these stellations as they strike the screen. Rutherford's early experiments were based on the use of such screens to observe and count the scintillations.
Progress in our knowledge of the mechanism of these transformations became more rapid when powerful electric methods were developed to count automatically the swift particles ejected during these nuclear explosions.
Improved apparatus to radioactive source could be measured. Inside the brass case is a single wire which serves as an electrode. Suppose that a radioactive source at the bottom of the case is emitting alpha particles. Is established between the wire and the outer case. The ionization caused by the alpha particles is collected, constituting a current to the central wire. Each alpha particle emitted ionizes the gas along its path into positive and negative ions, actually about 100,000 pairs of ions. These are pulled apart towards the electrodes in the same way as the ions in a solution being electrolyzed. The tiny charge collecting on the central wire as a result of continuous alpha particle emission can be measured. Development of radio valves enabled the pulse of current from each single alpha particle entering the chamber through a mica window to be amplified until it could operate a kind of counter. Then Geiger and Müller developed an ionization chamber which could multiply the original effect by a principle known as gas amplification. Here is a modern Geiger counter capable of counting at the rate of thousands per minute. Linked to it is an electric counter capable of high-speed recording. As the tiny speck of radium fitted to this rod is brought near the tube, the dials record the gamma rays from the disintegration of single atomic nuclei. These gamma rays are actually penetrating the walls of the tube, but charged particles can be counted by using a suitable type of tube. The ionization effect can be amplified and passed through a loudspeaker. so that each click represents the passage of a single particle, or as in this case, the ionization caused by a single gamma ray. The same voltage will operate an oscilloscope in which cathode rays trace on a screen the effect of these nuclear explosions. Such sensitive apparatus, atomic disintegration and studied, and accurate measurements obtained. About 1920, Aston, working at the Cavendish laboratory, designed this ingenious instrument known as the mass spectrograph. Positive particles or ions produced in the same way as in Professor Thomson's apparatus were allowed to pass through an electric field, which deflected the particles at varying angles according to their velocity. All particles of the same mass could be brought to a common focus on a photographic plate by means of a magnetic field of the right shape and intensity. In effect, Aston could weigh atomic nuclei very accurately. Work done with this apparatus showed that most of the elements accepted as indivisible by the chemist were actually mixtures of two or more substances of different atomic weights. The atomic weights of the elements had been very accurately determined by many chemists. Very few of them could be expressed as complete whole numbers. Aston showed that chlorine, for instance, with its atomic weight of 35.5, is in reality a mixture in a definite proportion of two forms of the same element, one with an atomic weight of 35 and one with an atomic weight of 37. Such different forms of the same element were called isotopes, and subsequent research has shown that the number of elements of which isotopes exist is very large indeed. Little by little, hundreds of experiments all over the world built up the store of knowledge about atomic nuclei. As time went by, experimental evidence and theory both emphasized the increasing probability that there did exist in the nucleus an uncharged particle of about the same mass as a proton. In 1930, Botha and Becker in Germany announced that they had noted what seemed to be an unusually penetrating gamma radiation produced by allowing alpha particles from polonium to bombard beryllium. The radioactive polonium gave off alpha particles which struck the beryllium. Radiation of some kind from the excited beryllium gave a high reading in the detector. Frederick and Madame Joliot-Curie measured the penetrative power of the radiation by inserting screens of varying substance. If these screens were of suitable density and thickness, most of them reduced the amount of radiation reaching the detector. But when screens containing hydrogen in the form of paraffin wax were used, a heavy increase of radiation was observed. In England, Sir James Chadwick confirmed the findings of the Joliot-Curie that this radiation consisted of protons. He suggested that the protons were ejected from the paraffin by an uncharged particle of about the same mass as the proton. Imagine that this billiard ball is a proton. No stream of light particles like electrons, no known type of wave, could have any more effect on such a body than these rice grains have on the billiard ball. But another particle of equal mass would share its energy on collision, just as this second ball imparts half its energy to the first as it pushes it away. A particle of unit mass, but without electric charge, and so very difficult to detect. Chadwick's reasoning recalled Lord Rutherford's suggestion of 1920, and the idea of a nucleus composed of protons and the uncharged particles, which were christened neutrons, was accepted. The field of force around the nucleus acts as a barrier against the penetrative power of charged particles. Neutrons, however, being uncharged, can penetrate these barriers and strike the nucleus. The majority of nuclei are much heavier than the neutron. If collision occurs, the neutron simply glances off and continues with a slight loss of speed. Now, paraffin is made up of carbon and hydrogen. Protons, or hydrogen nuclei, are no heavier than neutrons. So in a collision, the neutron is able to transmit a large amount of energy to the proton. This is the explanation of the proton radiation observed by the Joliot-Curies and Sir James Chadwick. The neutrons at once explain the existence of isotopes. Chlorine, for instance, has an atomic number of 17. That is, there are 17 electrons circling round a nucleus in which there are 17 protons. But chlorine has two isotopes. The atomic weight of one is 35, and of the other 37. If we add 18 neutrons to 17 protons, we get an atomic weight of 35. And in the 37 isotope, we have to add 20 neutrons to get the correct atomic weight. An isotope of hydrogen, called heavy hydrogen, has a nucleus consisting of the single proton of ordinary hydrogen plus one neutron. This nucleus, called a deuteron, has proved useful as a particle for bombarding atoms.
It became clear that to extend our knowledge, a more copious supply of bombarding particles of different kinds was necessary. Charged atoms of various sorts can be produced in vast numbers by the electric discharge through gases, and then accelerated by the use of high voltages. In this way, we have been able to obtain for our experiments in transmutation intense beams of protons and alpha particles, while the discovery of heavy hydrogen has given us a new projectile of remarkable efficiency in transmuting atoms.
Here at the Cavendish Laboratory in Cambridge, the experts of this modern alchemy of transmutation go about their business. The purpose of these huge electrical machines is simply to use electrostatic forces to accelerate beams of charged particles to very high energies, and with these atomic bullets to bombard the atoms of various elements in order to see what changes occur in their structure. This laboratory grew out of the converted lecture room where, in 1932, Cockcroft and Walton operated one of the first successful machines to produce high-speed particles and obtained significant results by bombarding lithium. The machine you see is a descendant of their original set. Ions are produced inside the large mushroom-shaped insulator and are accelerated down the rearmost tower. The bombarding tube continues down into the room beneath, where the stream of charged particles can be bent by a powerful magnetic field and directed towards a target. In the Science Museum at South Kensington is preserved the observation cabinet and accelerating tube of the original voltage quadrupler used by Cockcroft and Walton. Three cylindrical metal electrodes are arranged vertically inside a glass tube where a high vacuum exists. Protons emerged from a narrow positive ray canal at the top of the tube. As the protons descended, they passed through intense electrical fields by which they were accelerated and sharply focused. At the bottom of the tube, they struck the element set up as the target for bombardment. Any particle ejected from the target element passed through a mica window and caused scintillations on a fluorescent screen, which could be observed through a microscope. With lithium as the target, a startling result was obtained. Alpha particles of high energy were ejected. This result received wide publicity. Through the press, the public imagination was stirred by the vague implications of the phrase, splitting the atom. But to understand the significance of this result, it is necessary to appreciate one of the most important aspects of Einstein's theory of relativity. Let us hear Professor Einstein himself.
It followed from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is but equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Cockcroft and Walton in 1932 experimentally.
In quiet, non-committal terms, the scientists summed up their results thus. It seems not unlikely that the lithium isotope of mass 7 occasionally captures a proton, and the resulting nucleus of mass 8 breaks into 2 alpha particles, each of mass 4, and each with an energy of about 8 million electron volts. This reaction, which you see here, can be written down. We start with lithium of mass 7, placing 7 at the top left corner of the lithium symbol. Its nuclear charge is 3, so we add the figure 3 at the bottom left corner. The lithium is bombarded by protons, that is, hydrogen is added rather forcibly to the lithium, so we put down plus H. Hydrogen has a mass of 1 and a charge of 1. As a result of the reaction, we get 2 alpha particles or helium atoms, each with a mass of 4 and a charge of 2. Note that the 2 sets of numbers add up to the same on each side of the reaction. 7 plus 1 equals 4 plus 4. 3 plus 1 equals 2 plus 2. The actual masses concerned in the reaction are known from mass spectra. On the left, they total 8.0241 mass units. On the right, 8.0056 mass units. There is a difference of 0.0185 mass units. Measured in grams, this amounts to 3.07 times 10 to the minus 26. It is this amount of mass which has been converted into the energy released in the reaction. In other words, the relationship between mass and energy is a constant and is expressed in Einstein's equation E equals mc squared, in which energy is put equal to mass multiplied by the square of the velocity of light. So, to find the energy released, we substitute for m the amount 3.07 times 10 to the minus 26. And for c squared, we substitute 3 times 10 to the 10th all squared, which is the square of the speed of light in centimeters per second. Thus, the energy released, expressed in ergs, is the product of these values, namely 27.6 times 10 to the minus 6. Now, the energy of each alpha particle released in the reaction can be directly calculated. It is 8.5 million electron volts. Or, more conveniently, 8.5 MeV. Thus, in our equation, we get E equals the sum of these energies, that is, 17 million electron volts. Measured in ergs, this becomes 27.2 times 10 to the minus 6. Thus, one calculation gives 27.2 times 10 to the minus 6, and the other 27.6 times 10 to the minus 6, a sufficiently close approximation to show that Cockcroft and Walton were correct, and that great energy can be released by splitting the atom. Man had set his foot firmly on the road toward the unlocking of great knowledge and power. All over the world, atomic physicists sought machines of higher and higher voltage with which to reach a goal that was still hidden. This machine is known as a synchrotron. In it, electrons are whirled round at fantastic speeds by new methods of using small high-frequency currents combined with powerful magnetic fields. High-speed electrons cause gamma radiation, which is betrayed by this sensitive detector. Even a thick screen is easily penetrated by this radiation. Energies as high as 8 million electron volts can be obtained on this machine, and in the United States, electrons of 100 million electron volts have already been produced. Giant synchrotrons are now being built to accelerate positive ions. Hidden behind thick concrete barriers to absorb the dangerous gamma radiation is this latest type of linear electron accelerator, in which electrons pass through a series of alternating magnetic fields arranged in line along a corrugated tube known as a waveguide. Eventually, this machine will hurl electrons at its target with an energy of 5 million electron volts. Older in conception, but impressive in size and shape, is this electrostatic generator, designed to accelerate positive particles such as protons and neutrons. And this is one of the newest Van de Graaff machines to be built in England. These are so called after the American scientist who first designed them. Electric charge is sprayed onto a moving belt inside this tower and carried to the top of the accelerating tube, where the high potential thus generated is used to drive the particles down towards the target at great speed. When in operation, the machine is enclosed in a high-pressure casing, which permits a potential of 2 million volts to be built up. Most impressive of all in their suggestion of a Wellesian world are these 1 million and 2 million volt generators in the Cavendish laboratory at Cambridge. This is a cyclotron, one of the most famous of these accelerators. The inventor was Professor E.O. Lawrence of the University of California. The accelerating chamber or tank is fixed in the middle of the apparatus, between the poles of a very powerful electromagnet. The principle is ingenious. The tank, which is completely evacuated, contains two hollow D-shaped electrodes to which a high-frequency alternating current is fed. Minute quantities of the gas which is to provide the ions are admitted. The ions are produced in the center of the tank by electrons from the small arc or filament. Once produced, they are sucked into one or other of the Ds by the powerful electric field. But this movement of the ions takes place between the poles of a big magnet. Consequently, the ions will travel with a circular motion in the magnetic field. The alternating voltage accelerates the particles each time they cross the gap from one D to the other, so that they are whirled round faster and faster until finally they are led off towards the target by means of a charged deflector plate. Here, an element is being set up and bolted into the target chamber, ready for bombardment. Nowadays, it is known that almost all elements, if bombarded by neutrons, can be made radioactive for varying periods. Irene and Frederick Joliot-Curie first produced artificial radioactivity, and Professor Fermi made brilliant advances in this field. As the operator moves off towards the control panels, he passes through the water screens, 3.5 feet thick, which protect the scientists from the intense radiation produced by beams of accelerated particles. Now he begins to switch on the complicated high-frequency installation which feeds current to the Ds. To build and operate such machines, atomic physicists have to become engineers, overcoming step-by-step problems of high vacuum, screening from harmful radiation, construction of special magnets, and so on. For the production of neutrons, deuteron beams are usually found the most convenient. When the deuteron strikes the target, it splits up, liberating a neutron, which easily penetrates to the nucleus. At last, the full power begins to flow. Through the observation window can be seen the arc in the center of the tank, and round it the pulsation of the accelerating particles. Some idea of the neutron's effect on a nucleus can be given by this simple experiment. Imagine that the saucer is the nucleus of an atom. One might think that the neutron would go straight in and out on the other side, like this. Now let us fill the saucer with marbles to represent the particles in the nucleus. If we let the neutron marble roll down into the nucleus, it will jostle the others but remain in the saucer. The nucleus has captured a neutron. It becomes unstable and gives off its excess energy as beta and gamma radiation. If the neutron marble enters the saucer with a somewhat greater energy, one or more marbles will be knocked out. Thus, neutron capture can eject particles from the nucleus and cause disintegration. Outside the laboratories, the world was disturbed by the strident voices of evil men and the ever louder rumble of approaching war. But in 1939, atomic scientists made a fateful discovery. Professor Frisch, now at work in England, was closely concerned in this.
Early in 1939, Professor Hahn and Dr. Strassmann in Germany found that uranium, bombarded by neutrons, gave rise to what appeared to be an isotope of barium, only about half the atomic weight of uranium. Professor Lise Meitner, who had previously worked with Hahn and Strassmann, was by then in Sweden. It was he who told me of their puzzling discovery, and together we considered the possibility that the uranium nucleus sometimes broke into two halves. We found that such a process, although quite unexpected, was indeed compatible with what we knew about atomic nuclei. If we were right, a great amount of energy had to be released in such a process, and I was able to show this experimentally.
Hahn and Strassmann's evidence that a disintegration of the unstable uranium gave rise to elements such as barium in the middle of the atomic table was purely chemical and required a physical confirmation before it could be accepted. The uranium nucleus is unstable and radioactive, as is known from its ability to emit an alpha particle. If a uranium nucleus could indeed capture a neutron, becoming more excited and splitting into two approximately equal fragments, it was to be expected that a large amount of energy would be released in such a process, the fission fragments being hurled apart with great velocity. Professor Frisch obtained confirmation that this was so in an experiment essentially similar to the one shown here. Uranium was placed in the ionization chamber, which was placed over the end of a bombarding tube through which high-energy deuterons could be sent. The chamber was connected, as you see, to an oscilloscope. The trace you see here is made by alpha particles from the radioactive uranium. Now the high-tension set is switched on, and the uranium is bombarded by neutrons. On the screen of the oscilloscope, the fission pulses reveal the large amounts of energy released when uranium atoms are split. If each fission had to be provoked by elaborate apparatus like this for accelerating particles, there was no hope of deriving useful energy from the process. But each fission was found to be accompanied by the release of a few neutrons. One neutron had been used to provoke the fission. The fission itself produces more than one neutron, and is thus itself capable of provoking more than one fission, and so on. There is thus the possibility of a self-sustaining chain reaction. The reaction can begin without any neutrons being supplied from outside, since a few fissions are always taking place spontaneously. These would supply the fused neutrons. While these facts were being investigated, the political high tension in Europe sparked over into actual war. Years of aggression had at last forced the Western democracies to challenge the attempt at fascist domination of the world. Under wartime security, research on the use of atomic energy was pushed ahead. What was the problem to be attacked? The possibility of a fast chain reaction suggested an atomic bomb. There are two isotopes which make up the bulk of natural uranium. The atomic weight of one is 238, of the other 235. Over 99% of natural uranium is U-238. U-238 undergoes fission only with very fast neutrons. Many neutrons are scattered by uranium atoms and lose the speed necessary to cause fission. So, a divergent chain reaction will not take place in uranium, which is predominantly U-238. U-235, on the other hand, undergoes fission with neutrons of any velocity. It seemed possible that a controllable chain reaction might be achieved by using slow neutrons to cause fission in U-235. Using pure uranium containing both isotopes, a pile was built, in which uranium rods were embedded in a mass of pure carbon in the form of graphite. Neutrons produced in the uranium were slowed down by collisions with the light atoms of the carbon, the moderator as it is called, giving them a chance to cause fission in U-235. A slow, controlled chain reaction was achieved on December the 2nd, 1942. If natural uranium and a moderator were replaced by a small amount of pure U-235, slow neutron reactions would give place to fast neutron reactions. Fissions would occur, but so many neutrons would escape before hitting another nucleus that no chain reaction would build up. But if the amount of U-235 became larger than a certain critical size, a fast chain reaction would take place in less than a millionth of a second. This would produce a violent explosion. A simple mechanism for an atomic bomb thus suggests itself. Take two pieces of U-235, each smaller than the critical size, but which, if placed together, exceed that size. They are driven together, and so U-235 became bomb material number one, and its separation from U-238 became a war priority. The behavior of U-238 in a pile is also of great importance. Slow neutrons are sometimes captured by U-238. No fission is caused, but this nucleus becomes U-239. This is unstable. A beta particle is emitted, causing a change to a new element with different chemical properties, Neptunium-239. This new element is also unstable. Another beta particle is given off, forming another completely new element, Plutonium-239. Now, Plutonium-239 has fission properties similar to U-235 and will be built up by this process of neutron capture and subsequent beta disintegration throughout the uranium in the pile. Being a different element, it can be separated by chemical means from the uranium and used also for a bomb. So, plutonium is bomb material number 2. Huge plants for the production of pure U-235 and of plutonium arose in the United States. By 1943, it had become plain that Great Britain was fully extended in war production. In consequence, her nuclear physicists crossed the Atlantic to continue with American and Canadian colleagues the brilliant work already done. The main practical effort and most of its prodigious cost now fell on the United States, where very active research had been going on since 1939. The processes were laborious, and at all times elaborate precautions had to be taken by workers on the atomic pile and in the chemical laboratories because of the ever-present dangers from gamma and neutron radiation. Danger signs and warning signals, lead and concrete shields, remote controls, detectors, protective clothing. These were the everyday equipment of the men who worked to make the material for the bomb. At last, in the desert of New Mexico, the first atomic bomb was set off under conditions of great secrecy. Thousands of calculations, years of work reached their climax in this moment of dreadful splendor. Within a few weeks, the bomb burst upon Japan, and the news of it upon a startled world, which has now seen this supreme destroyer in action 5 times in all. We are aware now of the compelling urgency of the situation created by the bomb. We know that war must be banished, or else our civilization may die, as Hiroshima died on that summer morning in 1945. The tale has been told in full by those who lived through it. A city destroyed in an instant, 60,000 people dead, many from flash burns, thousands more by blast, many from strange sicknesses caused by gamma radiation. For a short while, the world was content to accept the fact that atomic energy, by destruction, had brought peace. Then came the question, can this power be controlled to serve mankind? Professor Einstein has recorded his opinion.
To give any estimate of when atomic energy can be applied to constructive purposes is impossible. What now is known is only how to use a fairly large quantity of uranium. The use of quantities sufficiently small to operate, say, in a car or an airplane, is as yet impossible. Presumably, all materials which may be used for such purposes will be among the heavier elements of high atomic weight. Those elements are relatively scarce because of their lesser stability. So, though the release of atomic energy can be, and no doubt will be, a great boon to mankind, that may not be for some time.
The core of the problem is to turn the atomic pile into a heat engine. The release of energy in a pile results in the generation of heat. If the reaction is allowed to run fairly fast, a cooling system is necessary to absorb the heat. To control the rate of reaction, rods of cadmium or some such substance must be introduced, which can absorb neutrons if lowered into the pile. Now, if the cooling fluid, probably helium gas, were passed through a heat exchanger containing water tubes, the water could be heated up and turned into steam. Most of this part of the installation would have to be screened off by heavy concrete or water shields and operated by remote control. The steam could be used to drive turbo generators to provide electricity in a powerhouse or in a big ship. This adaptation of the atomic pile as a source of heat energy is now being tackled in the United States and Great Britain. The use of radioactive byproducts from the pile is also being investigated. Medical research is now employing new tracer techniques based on radioactive elements. In this test, a radioactive sodium salt is being used to check blood circulation time. The Geiger counter picks up the radioactivity from the sodium. Now the doctor prepares to inject the sodium into a vein in the patient's foot. The radioactivity will be picked up by the counter as the sodium in the blood reaches the patient's groin. The injection is made and the scientist starts his stopwatch. The radiosodium travels up the leg in the blood stream. The counter is shielded from outside radiation by a lead block with a slot beneath. Now 10 seconds have passed and the counter reveals the arrival of the radiosodium. From such experiments it is hoped to devise a test to help prevent some of the complications which follow childbirth. Other possible sources of atomic energy are suggested by what is known of the generation of solar and stellar energy. Under conditions of tremendous heat and pressure, complicated nuclear reactions are provoked, resulting in the building up of helium nuclei from hydrogen. In this process, large amounts of energy are released. Perhaps man may one day obtain energy by building up heavier atoms from the lighter ones. Meanwhile, the representatives of the United Nations in conference strive for some formula to banish the atomic bomb and to permit the blessings of atomic energy to be used for peaceful ends. Great Britain's research establishment at Howell is under the direction of Dr. Cockcroft.
You have seen the story of a remarkable scientific achievement based on the work of scientists of many nations, but owing most of all to the work of Rutherford and the School of Nuclear Physics which he developed. The final achievement of the release of nuclear energy for war was due largely to the scientists and engineers of the United States, stimulated and helped by British physics. We have now the task of using the immense power of nuclear energy for peaceful purposes, for the production of radioactive materials, for medical and biological research, and for the generation of heat and power. With our present knowledge, it is possible to design nuclear power stations which will produce power at a moderate efficiency. Until we acquire operating experience of these plants, we do not know how economical they will be, nor are we sure of overcoming all the technical difficulties which will occur in a large-scale development of nuclear power. Nevertheless, there is a real promise that over the next few decades, world power resources can be greatly increased, and that the very great benefits to be obtained will do much to increase standards of living. It is a hope of every scientist that nuclear energy will lead to the establishment of a world organization for the effective control of all weapons of mass destruction, and through this to the abolition of war.
From Dalton's theory to atomic power. It is a long road, but the landmarks are clear. With the atomic theory as a basis, a pretty complete picture of the elements of our material world was fitted together during the 19th century. The discovery of electrons, the realization of the nature of positive rays, the strange powers of X-rays revolutionized conception of the nature of matter and of the atom itself. The study of radioactivity, first investigated by Becquerel and then by the Curies, led Lord Rutherford to make the greatest single advance in atomic theory. He pictured a small heavy nucleus in the atom round which the electrons revolved. In 1919, Rutherford discovered how to change one element to another by bombardment with alpha particles. He suggested that the nucleus of the atom might contain protons and uncharged particles of about the same mass. In 1932, scientists could say with certainty that the atom contained electrons carrying unit negative charges and a nucleus built up of protons carrying unit positive charges and of neutrons, uncharged particles equal in mass to protons, whose existence was proved by Sir James Chadwick. In 1932 also, Cockcroft and Walton split the lithium atom by bombardment with protons and found that mass could actually be translated into energy in perfect accord with Einstein's theory. Atomic disintegrations provoked by great machines became a commonplace of well-equipped physics laboratories. In 1939, uranium fission was first noted. The possibility of a self-sustaining chain reaction suggested the wholesale release of energy. Controlled chain reactions were achieved in the atomic pile. The imagination of the world has been stirred by the prospect of adapting such piles to use as sources of heat energy and as sources of radioactive materials for use in medicine. In research laboratories, the scientists are even now writing fresh pages in this unfinished story. But overall, the smoke of the atomic bomb hangs like a pall. If we are to reach the future that promises so bravely, the peoples of the world must see that this new power is wisely used.